All right, now remember that factoring means to introduce parentheses into it. Now in this case, we've done lots of different factoring. How do I know what type it's going to be? Notice this one starts with x squared. It is a quadratic. Whenever you see that quadratic, the odds are that you're going to end up with something that has actually two sets of parentheses in it. And this is the type that you're going to end up with here. And so each parenthesis starts with x, and then it's always just plus or minus some numbers there. The question is what those numbers are and how we get there. So what we saw on our last lesson, so in yesterday's work, we saw that we wanted to find out what two numbers add to the middle number and multiply to the last number. So in this case, adding to 14, multiplying to 24. And so mentally, I start going through the times table, and I'm looking in that times table in my head for 24. And I'm looking to see all the different ways I can multiply to it. So you might start in your head by thinking 3 and 4. And then you do 3 plus 4, okay, that's 7. That's not 14. That's not a winner. So I got to keep looking. Okay, what about 8 and 3? That adds to 11. Okay, so what else multiplies to 24? 12 and 2. That could be a winner, yes. And there are other options that you might have been checking. There are other options that we would check in there. But you end up with x plus 2 times x plus 12, or x plus 12 times x plus 2. The order of the parentheses does not matter, remember. Notice here, both of them are pluses inside here because I'm multiplying to a positive. And anytime you multiply to a positive, it tells you both signs must be the same. But that means they could both be minus or both positive. I know they're both positive because if they're going to be the same and add to a positive, then they both have to be positive for that reason. All right, so that is our final answer for that first one. Okay, now for the second one, we can do the same thing, right? We can say what two numbers add to the middle number and multiply to the last number. And we search through all the different ways to multiply to 16. Well, actually, I'm going to check one other thing first. If we're doing it this way, we start with x's. What will our two signs be? Plus, plus, minus, minus, or one of each? And how do we know that? Because a lot of people don't start by thinking about that, I've noticed. But if you do start by thinking about what the signs will be, it does make your life easier. Notice we're multiplying to a positive. If you're multiplying to a positive, that tells you that both signs must be the same. So it's either plus plus or minus minus. You then, in order to decide which of those it is, you look at what you're adding to. Since we're adding to a negative, it has to then be the minus minus. And so that's how you make that decision. It can make your life a little bit easier if you start there. That was a little bit of an aside, but I think it was worth it. All right, so now back to thinking about what multiplies to 16. Well, we tend to think of 4 and 4 here. A lot of our brains go there quickly. And what's 4 plus 4? 8. And I want an 8 there. If it's negative 4 and negative 4, that's a winner. And so yes, this would be correct. Except it's just not completely correct. Because in math, we're always wanting to simplify our answers as much as we can. And you'll notice that in this case, I have the same thing multiplied by itself. How do we write that something is multiplied by itself? Yep. We write it to the power of 2. That is, we square it. Because squaring something means to multiply it by itself. So while this is mostly correct, in order for it to be completely correct, it needs to be written this way. And yes, that also goes for wall map questions. When you see this problem come up on wall map, and you will, it needs it written in this form. Now, taking it back a little bit, in order to do this, I said what two numbers add to the middle number and multiply to the last number again. And yet, you could actually have done this one without having been here for yesterday's lesson where we learned that. Because, remember, this is that type that we saw before. This is that type that we saw last week, I think it was, maybe the week before, where we would go straight from that original to that form because it follows that pattern, where negative 8 divided by 2 is negative 4, and negative 4 squared is 16. So it follows that particular pattern. And so you notice we had already kind of used some of those skills before. It's just now you can see the broader scope of the whole thing, but you still have that skill from before, and it still works. All right, so this was just practice from yesterday's work. Practice with our factor. Now we got to get into today's new work. And today's new work is all about what we call number families. And number families basically are just different ways of describing numbers. It's another way of classifying numbers. Now, all the numbers that we're going to be working with today, and all the numbers we're going to be working with really all this year, fall into the family of real numbers. So they're all what we'd call real, which usually then raises the question about how can you not have a real number? You aren't going to need to know this, but I at least want to answer that question. Real numbers are the only ones we're working with this year. But the other type is imaginary numbers, also referred to as complex numbers. Imaginary numbers, I'm going to save those for next year's work. So they come up somewhat in Algebra 2. They also come up more in later classes past there. But basically, imaginary numbers occur when you try to take the square root of a negative number. So like the square root of 1, you know, if you punch that in your calculator freaks out and it says, I can't do that. It gives you an error. It's because your calculator can only work with real numbers. It can't work with imaginary ones. But that's what the imaginary numbers happen. That's how they happen. So when you try to take the square of the negative, there can be an answer, but only by getting into this other area. So that was just in case you're curious what's not real. So let's actually take a look at what the real numbers are. And go ahead and be writing this into your notes as we put it down. Leave yourself space as well, because I'll also give you examples of some of these kinds of things as we go as well. We'll put those in a little bit later. But you'll want to have these categorizations and their definitions in your notes. The picture we draw here as we're talking about it is a good way to do that. All right, so what we see here is that the family of real numbers, every real number is either rational or it is irrational. It's always going to be one or the other. So the entire family is split up into these two houses. Nothing exists outside of those two. Okay? So rational numbers, these are the ones that you tend to like the most. Rational numbers are the numbers that can be written as a decimal or a fraction. Notice specifically it can be written as a decimal or a fraction. That also means that it includes like numbers without decimals, numbers without fractions. All of those are also considered rational. Irrational are the ones that can be a bit of a pain at times. They're the non-repeating decimals. Now, when I say a non-repeating decimal, in other words, a decimal that goes on forever and never repeats itself. What's a good example of that? Yep, good. Most people think of that one right there. That's the most famous irrational number we have, pi. Because we can write down 3.14, but of course the whole decimal goes on forever. When we round it, we're writing a rational number. When we write the symbol that represents the entire decimal, that's an irrational number. All right, now, of these two families, if a number is considered irrational, we basically just stop there. We aren't going to break our irrational numbers up into more pieces. But there's lots of different types of rational numbers. And so we're going to look at more categorizations of that. The next categorization of rational numbers is integers. Integers are basically all of your numbers that don't have a decimal or a fraction in them. Now you'll notice then the difference. Every integer, and you notice the way it's drawn here is very specific for this reason, every integer is also a rational number. That's why this box is written within the side of rational. So every integer is also a rational number. But not every rational number is an integer. Like, for instance, if I gave you the number 3, that is an integer because it has no decimal or fraction attached to it. But if I give you 3.5, that's no longer an integer. By making it 3.5, we then kicked it out into rational. All right? Now, of integers, there's actually a number of different types. Because if we don't have a decimal or fraction, we tend to categorize that into positives, negatives, and zero. Well, that results in another categorization within. A type of integer is a whole number. Now, when we say whole numbers, we actually have to be very specific here. Whole numbers are the ones that have no negatives in them. And as you take a look at this, you'll notice that the whole numbers group here, it is built entirely within the integers group, which means that it can only be a whole number if it's already an integer, which means that whole numbers have no negatives, but they also have no decimals and no fractions. All right? So, let's say you have a number. Let's again go to the number that I pulled out earlier, 3. 3 is a whole number. Since it is a whole number, it is also an integer, and it is rational, and it is real. It is all of those things. If I made it a -3, all of a sudden that's not a whole number anymore. A whole number has to be positive. If it's -3, that's an integer then. All right, now these are some examples of each of these different types of numbers. So first of all, let's take a look at the rational numbers. Rational numbers. You'll notice that all of these numbers are considered rational, but some of them are also integer or whole, but that doesn't mean they're not rational. So for instance, like 52 here. 52 is a rational number. Yes, it's also an integer and it's whole, but it is then an example of rational because anything that is an integer is also rational. Remember, rational numbers can be written as decimals or fractions. You notice here's a decimal, -1.93. Okay, it's a decimal, so that's rational. What about this one, 15.8 repeating? Sometimes this type throws people off a little bit because that decimal goes forever. But by repeating, we can actually write it. And remember, that's the critical thing, is we can write it as a decimal. By putting that little line over the 8, I can then actually write that down. Therefore, it is rational. 2/7. If you take 2/7 and put in your calculator, it's going to look like a really ugly number. And you might think, just looking at that decimal in your calculator, that it's going to go on forever and never repeat. Technically, actually, it will repeat. But since we can write it as a fraction, we can write it. Therefore, it is also considered rational. So notice what the flip side of that is. Irrational numbers, pi, we mentioned that one earlier. But also, the other way that you can get irrational numbers is by trying to take the square root of something that gives you a never-ending decimal. So like the square root of 2, since it's not a whole number, it's going to be a decimal that goes on forever. So that's the way we get irrational. Now you notice I didn't give you any specific examples of real numbers. That's because everything that we see here is real. So everything you can come up with as an example is going to be a real number. Now breaking it down a little bit more as we go down that list, you notice integers, they cannot have a decimal or a fraction with them. So basically this is a list of all integers. If we continued this pattern going forever to the left and forever to the right, that's what the 3 dots mean, is it just continues following the same pattern. You'd have a list of all integers. Granted, it would be infinite, but it's basically a nice representation of the whole list. Notice our integers, they can be positive, they can be 0, they can be negative. Our whole numbers, remember, they cannot be negative. And so it goes on forever as we go up, but you'll notice there's no 3 dots here on the left side. That's on purpose, because the list does not go down further below 0. It actually goes down to 0, and then it goes up from there. Nothing to the left, because it can't be negative. So all of these are different examples of those types of numbers. We're going to practice those ideas of classifying numbers with these three examples. Now notice what the instructions say here, because we've got to pay attention to that with these problems. In this case, it says classify each number according to its most precise number family. So our answer is going to be just one number family, and no, you can't just say they're all real. It has to be the most precise number family. All right, so let's actually take a look at how we would classify each of these, because I'm not doing a ton of examples, so we'll get an opportunity to look at some subtleties along the way here as well. So first one, we have negative 1073. All right, first of all, the thing that leaps out to me first is that there's no decimal or fraction involved. So already, I've got narrowed down to only two possibilities. It's either, at its most precise, an integer or a whole number. Well, it's negative. Since it's a negative that does not have a fraction or a decimal, then we call it a what? Yep, integer. It is an integer. And yes, we say integer, not integer. It's an integer here. Integer, remember, means it can be negative, but no decimals, no fractions. So that's the most precise it can get. You might be thinking, well, isn't it rational? Yes, it is rational, but integer is more precise than that. Integer is a more narrow, focused categorization. And it cannot be whole because it's negative. All right, number two. Some of you might be thinking irrational here because you're seeing the square root. And one way to get irrational numbers is to take a square root. But you always have to look at the number and see, if I take the square root, what do I get? The square root of 25, it actually equals a nice pretty number, right? It equals 5. So the number that we're actually categorizing then is 5. Okay, I'm looking at 5 there. No decimals, no fractions. It's positive. What's that make it? Whole, absolutely. So that is a whole number. That's the most precise. Yes, it is also an integer, but whole is more precise. So we have to use whole as our way to categorize it there. Okay, number three. Number three can be a little bit extra tricky. We're going to see if I tripped you up here. In this case, as we take a look at this decimal, I know a lot of you are saying, it's pi, but it's not pi. Pi is actually 3.14159 and more. Pi is the entire decimal. Pi requires that this is the decimal that goes on forever, never repeating itself. But what I wrote down is a decimal. It is a rounded version of pi, yes, but it is not pi. It is rounded. And since it is rounded, this decimal stops here. Therefore, I can write it down. After all, you can see I wrote it down. So if we can write the decimal, what do we call it? That's rational. See, that one's tricky because you actually have to look at it and think, is it 3.14159 or is it pi? And in this case, it is just 3.14159. It's not the whole decimal, it's just that piece of it. All right, so having done each of those, we're now going to do one more set of practice problems. Now again, we always have to read the instructions with each of these. So check what this one asks us to do. Identify all families to which the number family or which the number belongs. So in this case, many of your answers, actually all of your answers, will have more than one word written down. All of them will be more than one number family. All right, so let's take a look at number 4 then. First thing we got to do is know what the square root of 99 is. We got to kind of know what kind of number we're looking at there. So you might know off the top of your head, if I take the square root of 99, is that going to equal a nice pretty whole number? If you know the answer to that, go with it. If you don't know, then you plug it into your calculator to find out. And when you plug this in your calculator, you're going to get a decimal. It's like 9.9 and a bunch of decimals after that. Since we took the square root and got a decimal that just keeps going, that tells us that this is an irrational number. But we're not done there. Because again, remember in these, we're identifying all of the families to which the number belongs. And every irrational number is also what? Well, what is every number? Every number that we've been looking at is real. And so the square root of 99 is irrational, and therefore it is also real. All right, number 5. And again, seeing if I can maybe trip you up or show you some new things, show you something that might have tripped you up if we didn't talk about it, that sort of thing. In number 5, you have 3.00. Okay, is that a whole number? Yes, it is. And some of you are looking at it going, wait, it's got decimals on it.
No.
Yeah, but it's 0.00. What does 3.00 equal? 3. Kind of like when we had the square root of 25. I figured out, okay, what's that really equal? That equaled 5. And so I used 5 when I did it. In this case, 3.00 equals 3. So that's the one I'm working with. Now, what's the most precise way to categorize 3? So yes, the most precise way to categorize it is as a whole number. But of course, we don't stop there. Every whole number is also what? What's the next level up? Well, if it has no decimals or fractions, it can be whole or integer. And so every whole number is an integer, so I put integer down as an option. And then every integer, if I take a look at my picture, every integer is also rational. And every rational number then is also real. And so you notice that these types, where we got to categorize every number family, it can sometimes be a bit more involved. All right, and then we go on to our last one, number 6. It's 2/3. It's a fraction. Now, does that fraction equal a whole number or anything like that? No. 2/3 is just 2/3, or it's 0.6 repeating if you wanted to think about it that way. What is the most precise way to categorize that? It is rational, yes. And therefore, if it's rational, it is also real. Because, of course, all of these numbers are real. And so we need to account for every single one of these. So remember, as you do assignments that involve these types of problems, as you're doing work that involves these, always pay attention to what you're being asked for. Are you just asked for the most precise, or are you being asked to give all families? Because, of course, your answer is going to change greatly depending on which type it's asking for.